So that's our popular three methods. So those methods have different attributes in terms of deployment and operating costs, in terms of temporal, spatial resolutions, and coverage. Over the past several decades, there were billions of dollars investment in telecommunication infrastructure. So about 10 years ago, I started thinking about using this infrastructure besides telecommunication. What else we can do? Particularly, say, if it's possible to use the infrastructure to measure the rain, for example. So can we achieve some advantage by using those infrastructure? For example, low cost, high temporal spatial resolutions, in particular for micro scale or farm scale measurement. It turns out that this is possible because in particular for wireless communications, we use microwave signals to transmit data. When the wavelength of the microwave signals is close to the size of a raindrop, which is a few millimeter. So then there will be scattering, there will be absorption of the microwave signals by the rainfall. So this is called rain attenuation. Rain attenuation are related to the frequency of the microwave signals, related to the rain, for example, raindrop size distributions, environmental temperature, etc. So in general, the higher the frequency, the severer the rain attenuation. And a common model to describe the relationship between the rainfall rate and the rain attenuation is this power law relationship. If you are familiar with weather radar using so-called radar reflectivity factor psi, and that psi, the relationship with the rainfall rate also follow the power law. So that means that we could, using this power law, to retrieve the rain rate. It turned out such work has done before, and I was 10 years ago, I was aware of work by a research group in Israel. So they published a paper in Science in 2006. So they using the macro links of backhaul cellular communication system to measure the rain. As we know, our mobile phone, to work, the mobile phone needs first to talk some towers, we call base station. And between base station and some center, there could be fiber optic, there could be microwave links. And in Europe, and also somewhere in Australia, I believe they are using microwave links. The signal strength of those microwave links are normally stored in the operating center by the operator for maintenance purpose. So that's why those Israel group, those researchers say, since those information available, why we use it, and they use it to measure rain. So they reconstruct the rainfall in 2 cities in Israel. And then people follow on, and when exemplar work was published in 2013 by a group in Netherlands. So they use thousands of macro links to retrieve the rainfall map of the whole country of the Netherlands, so which was significant. But there are some issues with those backhaul links. So first thing, the accuracy and sampling frequency is quite low because the purpose is to use for maintenance, it's not to measure rain. Another thing is it's 2-dimensional. It's on the ground. So that's why about 6 years ago, I started the idea is why we not using the low Earth orbit satellites to measure the rain. Today, there are essentially 2,000 active low Earth orbit satellites. And in the future, there are more to come. So a particular example is the Starlink, and they are quite ambitious. So they want to launch about more than 40,000 LEO satellites. And to date, I think there are 1,400 operational now. The key point is the user terminal for the Starlink. The first thing is small, so the antenna is about 60 centimeters in diameter, and also cheap. I just read the news say that it's, nowadays it costs $1,500 to make each piece, and of course customer pay less because it requires the cost from the when you ongoing use it. So so the customer pay about $500. If we're using the LEO satellites, since the LEO satellites would move around the Earth, so it's just like you go to the hospital. Sometimes we can do a CT scan and the tube rotate. So essentially you can retrieve the 3D structure of the human being body. So similarly, we can do when the LEO satellites rotate around the Earth, so you can reconstruct the 3D structure or whatever happened in the atmosphere, in particular the rain. Using signals from satellite to measure things in the Earth, in the atmosphere or on ground is not new. So for example, for medium Earth orbit, that's typically the GNSS satellites, so for example, GPS satellites, people already use it to measure the water vapor. Because GPS or GNSS signals is L-band signals. That L-band signals, the water vapor would impact the refractive index N of the propagation of the L-band signal. So therefore, it would impact the propagation delay of the L-band signal. Using that, if the receiver you put on in space, the satellite receivers, you can measure the radio occultation. So based on that, you can reconstruct the water vapor. Or you put on ground, so it's still, you can reconstruct so-called the column water vapor. And another way to using the GNSS signal is called GNSSR. In this case, you need two receivers. One receiver you point towards the satellite itself, another receiver to point anything you want to measure. So by using this, you can do measure the ice, ocean state, soil moisture, etc. And people put GNSSR on ground, on airplane, or in space, in satellite. So people do all different things. Also for geosynchronous satellites, for example, DVB-S, and in Europe, people start using it to measure the rain. And even people propose so-called active LEO satellite, means that people propose to launch satellites to emit particular microwave signals to the ground and using ground then to detect things in the atmosphere. But still to be launched, and people propose the idea by NASA and NISS. The idea popped up in 1998, but the active LEO satellite was not launched yet. So for more than 20 years, not launched yet. So I think it's simply too expensive to do that. So my idea is to using existing LEO satellites, the signal from existing satellites to do something. So we were talking about, today I'm talking about the potential of the proposed method. Particularly, I want to compare the proposed method with weather radar, and also the details of the principle of the proposed method, and give some results. Then I will be talking about to measure things beyond the rainfall. First thing, in terms of potential of the proposed method, I think the first thing is low cost. So the satellite is not using existing satellite. So it's opportunity signals from existing satellite. And ground receiver is passive. Unlike weather radar, you do not need to emit signal. You just receive signal. Also, most components of the receiver should be available off the shelf. So you just reuse the signal, whatever the SpaceLink, the SpaceX use. And another thing I want to highlight, as I will mention, that some parameters, unknown constant, you do not need to do the online calibration, unlike the weather radar. Weather radar, you need, I guess, every month, you need to go to the field, you need to do the calibration. In our case, the calibration is done in some center, so you just need to resolve those unknown constants. The second potential is it could be reconstruct the three-dimensional structure. And particularly when using the LEO ground receiver, the ground receiver normally is working in high elevation angle. So the interference from the ground or the ocean should be small. And since the cost is low, so we could deploy a large number of ground receivers, therefore increase the spatial and temporal resolution. And also, because it's new, so presumably you could accommodate the rainfall measurement requirement into the implementation of the ground receiver. So we could customize the receiver if we do it now. So that makes the accuracy of the data to be higher, and also you get a higher sampling frequency. So a little more about the peripheral method. Firstly, about the coverage. So because it's at the minimal elevation angle for ground receiver, so it can only cover a space of cone. So normally the range height is about 4 kilometers. So if the minimal elevation angle is 5 degrees, so you can compute it's about 90 kilometers in diameter. Normally SpaceX would work on minimal elevation angle, I think it's 40 degrees. So that's effective, 40 degrees. So that's about 10 kilometers in diameter at the range height. So if we do multiple ground receivers like this, still there will be some gray zones there. So that's the coverage range. So I already talked about 3D observation of the rainfall. It turns out for meteorology, it's very important. So how important, I just gave 2 examples. One example, people measure the 3D structure, in particular the vertical structure of the atmosphere. The meteorologists using radio sounder networks. So in the USA, I don't know that 92 sites. Each day you launch 2 balloons, and each launch it costs $325. So if you do the calculation, 1 year, about 21 million per year. And globally, there are 900 sites. And if you're using the cost of USA, that will be 200 million per year. So it's recurring cost. So every year, so you just throw 200 million away. And another thing that can measure the vertical structure of the rainfall is called GPM. So it's a satellite. So basically, you put the weather radar on the satellite. So that's a program by NASA and Japan. So it's about 400 kilometers in orbit. So there's 2 precipitation radar there, the Ku band and Ka band. The whole program is $1.2 million. If you use that $1.2 million, and if you think about the LEO ground receiver, the cost, let's say, about $1,000, so it means that 1.2 million can be used to purchase, to deploy 1 million ground receiver. So if you low cost really matter. So now let's compare a little bit between the weather radar and the peripheral method. So weather radar measure the radar reflectivity factor, both horizontally and vertically. And also it can measure the Doppler velocity if the Doppler weather radar, and also the spectrum bandwidth. The proposed method, we measure the ring attenuation in both polarization. Also, we could measure the power spectral density. And weather radar is active, it emits signals, and the proposed method is passive, just listen. Weather radar is passive. One weather radar is about $1 million, and the proposed one, the ground terminal, the ground receiver will be in the order, I think, a few hundred meters to $1,000. And weather radar, since it's active, so the same signal, same band of signal cannot, so the same radar cannot be deployed in the same area because that would interfere with each other. But we just listen, so there's no interference. And the weather radar is normally work in small elevation angle to extend the coverage range. So therefore, there will be interference from the ground. But peripheral method normally work on large elevation angle. And weather radar on lower frequency band, for operational weather radar, it's normally working lower band, S band, C band. And for our proposed method, since we're using the communication satellite, so it's normally higher band. And for Starlink, I think we use Ku, K, and V band in the future. So the potential application of the proposed method, first thing is it would contribute to climate and weather models. In meteorology, in particular in some area, the data are really not available. So a particular area, the meteorology is called maritime continent. That's Indonesia. Indonesia, there are a lot of islands and the oceans. So those islands, it's really hard to get data there. So it's very difficult to deploy weather radar there. But if we have this small receiver, it could be easily deployed there. So that's essentially you fill in the data gap. And also, if we deploy a lot of ground receiver, potentially we increase the temporal spatial resolution. And also can be applied hydrology and climate extremes. In particular, for example, tornadoes. So always 3D structure. So it's desirable to get the 3D structure. And in other areas I want to highlight is the renewable energy. So renewable, when we talk about renewable energy, the big part is about the solar energy and wind energy. They are all related to weather. And of course, if you do something fancy, you can do so weather modification. If you know the process or meteorological process, then presumably you can modify it. Let's say increase the rain or reduce the rain, etc. So let's now talking about the key idea behind the proposed method. The first step is you divide the three-dimensional rainfall field into multiple cells, each cell associated with the specific attenuation variable. Then you, at ground receiver, you measure the signal to noise ratio. So every time you measure signal to noise ratio. And signal to noise ratio relate to 4 variables. The first variable I call the constant C. By constant, I mean that when the satellite is overpassed, for one overpass, the parameter does not change. Relative does not change. For example, the transmit power, the antenna gain, and also the thermal noise. So if it does not change, then I treat it as a constant C. The second term is free path attenuation. So free space path loss. So free path loss is related to the length between the satellite and ground receiver. So that's the second term. The third term is related to the specific ring attenuation. So basically, you from the satellite to ground receiver, across multiple grids or cells, and each cell we assume is unknown specific attenuation variables. So you multiply with the length, the intersection of that cell. So then you do summation together, you get that the path ring attenuation. The third term is the environmental noise, or I call space noise. This space noise is related to ring attenuation. So that's why it's not constant. So then, given the price of the specific attenuation variables, we have, so let's assume we have some information about the specific ring attenuation variables. Then based on this formula, we can formulate the optimization problem and solve it to get the value of the specific attenuation variables. So then it's up to the meteorologist to determine. So you use that based on this to interpret what phenomenon happened. So that's the basic idea. So first thing, why we use signal to noise ratio. And here is the typical digital receiver. Normally in the digital receiver, you would have the ISSR. And commercially available ISSR normally is in a precision of 0.1 decibel. It works, it could work, but we want to do better. So in terms of SR, I will talk about later. So we can achieve, in terms of precision, we can be 0.01 decibel or better. So that's why we want to using the SNR. So 0.01 decibel is important because if you look at the frequency under the attenuation of microwave signals, for light rain, let's say 1 millimeter per hour. So that's the attenuation is a few 0.1 decibel. If medium rain, that is actually 1 decibel per kilometer, and if it's heavy rain, it could be 5 decibel per kilometer. But if you want to measure other things like cloud or fog, it's essentially in the order of 0.01 decibel for key band signal, the 30 gigahertz. So that's why the precision is higher, is better. So in terms of the signal to noise ratio estimation, we know that from estimation theory, it's related to your observation window, the length of the window. So the larger the window, so basically you have the better the SNR estimation. However, for LEO satellite case, because the satellite is moving, so the SNR is always changing. So how we set the window length? Our idea is that because from estimation theory, even using a window length, that's still estimation error. As long as the impact of the estimation error is larger than the impact of the SNR variation because of the movement of the satellite, then we just using the estimation error as the error for your SNR estimation. So here is one example. So when increase window length for a particular setup for elevation angle 40 degrees, when the window length increase, we use kilometer bar or mean square error to measure the performance of SNR estimation. So window length increase, the mean square error would decrease. On the other hand, when the window length increase, the ring attenuation of that part would increase. And that's for heavy rain, and that's for light rain. And also the free space path loss. So the change to the SNR would increase. So we found that the cross point is here about 0.06 seconds. So that's why we choose the window length of 0.05 second. So we're using the MSE or chromiral bond to indicate the performance of the SNR estimation. So that's for elevation angle of 40 degrees. And if you elevation of angle of 90 degrees, so that gives this figure. The point I want to make is the SNR estimation, if you look at the performance, so at 0.05 seconds, so the chromiral bond is in the order of 10 to, so that's 16 months. So it's here it's about 10 to minus 4. So essentially it's about 0.01 decibel in terms of precision for the worst scenario, that is the lowest elevation angle, which is 40 degrees. So now about the unknown constant C, there are two ways to resolve it. One possible way is just treat as unknown variables. Then use your optimization algorithms to solve it. Another way is to using a so-called differential measures. So because C can be assumed to be the same constant if the time k and time k plus 1, the time difference is very small. So you can assume C does not change. So you can essentially use the two equations. So you minus to do the differential, then you cancel out that C. So then in that way, so no online calibration is required. So it's everything done by center. So you deal with this unknown constant C. So how about the free space path loss? So this is related to the distance between the LEO satellite and the ground receiver. So that's called LS. It turns out that the location of LEO satellites can be very accurately determined. It's in the order of 0.1 meter. And actually for a window 0.05 seconds, the LEO satellites move about 300 meters to 400 meters. So 0.1 meter is trivial. So we can use this formula to compute the free space path loss. So that's why this is assumed to be known for our system. Now about the space noise or environmental noise. It's related to the raining attenuation. Why does it happen? Because it's based on black body theory. So anything in black body, if it in thermal equilibrium, whenever it receives energy, it must emit that energy. So when it emits energy, that's noise. So that's why it's related to, because attenuation means that it absorbs energy. So it's emitted, so that's the environmental noise. The ratio between the environmental noise or sky noise with the raining attenuation for particular path is given by this formula. So the raining attenuation as a particular path related to the noise temperature, which can be used to compute the noise power. And here Tm is simply the environment, the temperature, the environmental temperature. And for the receiver, you're using a receiver antenna, and antenna have a beam form. Right? So to compute the space noise temperature, you simply do the average of the beam form, and then that's the temperature picked up by the receiver. So that's the mechanism behind the sky noise. Okay, now the sixth model is like this. So what we do is we move everything unknown to the left-hand side of the equation. So the raining attenuation, the spectral raining attenuation is unknown, so we move to the left-hand side, so which is basically a linear combination of the raining attenuation, spectral raining attenuation variables, and multiply with coefficients of the intersection of each cell. And the unknown constants let's assume it's unknown. So let's move to the left. Anything on the right is assumed to be known. So signal to noise ratio is measured by the receiver. So I denote by rho hat k. So move to the right. And since the satellite location is known, so we know the, by the way, the ground receiver is assumed to be fixed on ground. So the position also known. So the free space path loss is known, move to the right. And we're using iterative axioms. Initially, we assume the ring attenuation, there are some initial values. Therefore, the noise power or the space noise assumed to know. So we put it here. So then you find that it's just a linear equation. Right? So linear equation and unknown is alpha, so which represents this all specific ring attenuation of each cell, and plus this unknown can see. Right hand side is everything known, so denoted by xk. So it's actually a linear equation. So to solve this problem, to solve the, we can using a iterative algorithm. First, we assume that sky noise power is 0. Then we solve the least square. We're using least square to solve the problem. So essentially least square with non-negative constraints. So that's the least square problems. And then with all the special ring attenuation and the constant assumed to be non-negative. So we solve this problem, then we get the specific ring attenuation for each cell. So based on that, the sky noise we call is related to the ring attenuation. So we can, using the ring attenuation, then to reconstruct the sky noise. If you reconstruct the sky noise, then this equation would change, right? So that's why you go back, you need to solve the least square problem again, and so on and so forth until you stop, right? So based on this, we did some simulation. So first thing, example 1, we're using K-band signals, 30 kilohertz, and one satellite only. And the orbit height is 1,000 kilometers, minimum elevation angle 40 degrees. The overhead time is about 300 seconds. It's 280 something. And on the ground, we assume that we deploy a lot of ground receivers. So essentially the distance between ground receiver is about 1 kilometer. And the minimum SNR at the receiver is we set at 13 decibel. For each ground receiver, we assume that 150 data points available. Each data point is the measured SNR for window length of 0.05 seconds. And in terms of the rainfall field, we're using a WRF simulation. WRF is the software used by meteorologists. Simulate storm in the Great Reef area. So based on that rainfall process, we simulate the signal at the ground receiver, including everything, the thermal noise and the space noise. So here's the result. So this is the original data. That is the WRF simulated rainfall process for a vertical slice. Then we run our iterative axiom, first iteration, second iteration, third, fourth. We find that the result is always oscillate between even iteration and odd iteration. So that's why the result effectively do the average between the third and the fourth. So that's we treat as final result. It can be seen that it's quite close to the original data. And this is a 3D presentation of the result. So that's the original rainfall process. And then this one is a retrieved one. So we also use the differential measure to deal with the unknown constant. So the result will be similar. The first iteration, second, third, and fourth, and the average of third and fourth. We can say it's the original one and the reconstruct one is quite similar. Here, I want to highlight, for example, one, the number of data points or the number of observations for one vertical slice is essentially 150 data points plus 32 ground receivers. And the number of unknowns is essentially for horizontal is 20, and vertical is 35. So if you do the calculation, the number of data points available divided by the number of unknown variables, that's the specific range attenuation variables, is 7 times. Later we will talk about compressive setting. So we're using less of observations than the number of unknowns. So by using sparsity of the rainfall image. We give another example. Everything the same except the ground receiver is randomly located. I think exactly the same. And we look at another rainfall process. This time called localized frontal rainfall. So we did that. So again, the result is similar to the original data. So as I mentioned, the rainfall process should represent some sparse property. So that's why we also using a particular compressive sensing algorithm try to retrieve the original rainfall process. So the rainfall is the same as example 1. The number of ground stations for a 2D area is 20 by 15. And this time we do for 2 cases. One case we're using one satellite, one LEO satellite. Another case is using 10 satellites. It's simulated by, it's done by STK. It's actually the Starlink satellite. So at one moment you can see 10 satellites in particular areas. And we're using snapshot observation, means that unlike the first 2 examples, in this time, it's just for one time, just using the data points at that time, we reconstruct the rainfall field. And particularly even for 10 satellites, the number of data points we use divided by the unknown is 1/5, because there are 10 satellites. The 10 satellites and the data grid is 20 by 35. The data, if you look at the slide, and the horizontal is 20 cells, and vertical is 35 cells. So if we do the calculation, you eventually find that if you use 10 satellites and the number of ground stations horizontally, I think we're using 20 ground stations. So if you do the computations, so essentially the number of observations will be less than the number of unknowns, the 1/5. The result, I would not say it's as good as before, but still you can say that there's something similar between the reconstruct image and the original image. Okay, so far the 3 examples is all about simulation. It's using synthetic data. We also did one case using field measurement data. So this is in 2015. We used the ground station in it's a Miyun ground station in Beijing. It's for a particular low Earth satellite, it's one satellite. That satellite, the elevation angle range for that case is 5 degrees to 33 degrees. So ground station using a big antenna. So that's why it can handle low elevation angle. Again, the system is not tuned to us. So the quantization precision was 0.5 decibel and 15 samples per minute. Since we're using only one satellite and one ground station, actually it cannot recover the rainfall field. So to recover it, you need some interpolation. So we're using interpolation in Gaussian, with the Gaussian radian basis function. Then we did the work. So this recovered rainfall field, rainfall map on the ground. It's a two dimension. By comparison, we using the so-called rainfall product. It's called GSMAP-NRT. So that's rainfall product, global rainfall product, tells you everywhere in the world what's the rainfall. So we're using that. So actually, that product only giving you 1 hour average of the rainfall. So that we use that as a reference. And our recovered one, because the satellite is overhead about 10 minutes. So it's just for that 10 minutes. But still, you can say that the rainfall center is very similar. So the point is that using field measurement data for one VLS satellite and one ground station, we could still produce something useful. So that's about rain. And we also done some work beyond the rain. So one thing is about cloud. So there's some difference between cloud and rain. The first thing, the attenuation is much smaller than the rain. But on the other hand, the altitude of cloud normally is higher than the rain. So the black spot, the coverage, is not a problem with the proposed method. Also, the required spatial resolution is lower for cloud than the rain. Normally, it's lower. So we did some work and published in the atmosphere. So this is the cloud one. So you can say it's quite similar. And another work I have done is to using the microwave signals from LEO satellites to deal with flying objects. So flying objects such as airplane, drones are very different from rain or cloud. The key difference is that in terms of the propagation of microwave signals, you need to consider the diffraction effect because the flying object is so small. So, but there are some good things. So first thing is normally when you consider flying objects, so what you need to consider is the flying object can only impact the propagational signal when the flying object is close to the link between the satellite and the ground receiver. For such a case, because the received signals would be determined by the silhouette of the flying object, it's not determined by the reflection or determined by the scattering. So it somehow it's still immune. And particularly we did simulation when a flying object goes across the links between the satellite transmitter and the ground receiver. For Ku-band signals, the received signal would fluctuate significantly. So here it's about, I think about more than 20 decibel in terms of the received signal change. But for very, very short period, it's about 0.2 seconds. So basically, the closer the flying object to the link between the satellite and ground receiver, the more fluctuation of the received signal. So based on that, actually you can do the positioning or the time variation or the received signal. So that's what I recently published. So far we have done some work in using macro signals from real satellites to detect things in the atmosphere. But those work, I have to say, are still very preliminary. So first, the algorithm we use are actually very heuristic. So it's not optimized. As long as we just find the algorithm that could work, so we tried, it worked. If worked, I mean, we just presented it. And second thing, the information of the ground receiver is just the SNR. There could be other information available, for example, the polarization information, SNR for vertical polarization and vertical and for horizontal polarization. Also, for our work, we just do some, I would say, ad hoc work. It's simulation. So that not really some solid theoretical work. So I think that in the future could be, for example, resolution analysis, also how to deploy the ground receiver, the location of the ground receiver. Another thing I want to mention is we collaborate with people who work on the atmospheric sciences. But I would not say collaborate, it's really cooperate. So essentially they produce some data and they pass to us and we process it. So that's it. But in future, I hope it could be really collaboration. So we work together, say we improve the numerical weather prediction, we do data simulation, etc. Or we can measure some other things relevant to the atmosphere, say water vapor, aerosols, dust storms, etc. I think it's still possible to do that. Another thing is, so far, our main work is about simulation. So in the future, I hope we could, using more field data, say using Starlink ground receiver, measure data, use those data, and then measure with, do some comparison with whatever measure, say, by the weather radar. And also in terms of things beyond meteorological variables, in particular the airplanes, drones, and birds, and things become very different. You need to consider the diffraction effect. And but what's good thing I think is because using LEO satellites, the link is always moving. Because it's moving, so there's always relative motion between the objects in the atmosphere and the link. So if you think about moving, then from radar term, there's so-called synthetic aperture radar, the SAR, or the inverse SAR. So using the similar idea, potentially you could do the imaging of the things in the atmosphere, for example, airplane, drone, the bird. Of course, I do not expect that the image will be very good, but still you recover something, you still can tell you something. So that's the publication we published so far relevant to the topic I'm talking in this seminar. And another thing I want to acknowledge my collaborators, so both from UWA and out of UWA. Without them, I think the talk today is not possible. And I also would like to acknowledge the support of ARC Discovery Program. Okay, that's all for my talk. Thank you for your attention, and